Yeah, so I think we had summertime when I made the schedule, and as I understood, China is not changing time between summer and winter time. I think that, but yeah,
Well,
otherwise the
European,
US was impossible to join as well. And I should apologize to all the poor Australians that have a hard time following the conference.
It's okay, yeah.
I think we should get started. If you're ready, Paula.
Of course I am. Thank you.
Yeah. Then I would like to welcome everybody for this second day of FM. And it's my great pleasure to introduce Paula Herber. So Paula is a professor at the University of Münster, where she's heading the Embedded Systems group. She's also since recently part of the Formal Methods and Tools group at the University of Twente, where I have the pleasure to collaborate with her. So Paula obtained her PhD in Berlin in 2010. And after that, she's been working in various places. So she has been again in Berlin, but she's also been in Berkeley, she's been in Potsdam, and since 2018, she is in Münster. And there she's working on I would characterize it as using formal methods and different kind of verification techniques to apply for embedded systems, and really looking at how these techniques can be applied for people working in automotive industry or other kind of practical embedded systems. So this is really about how to make formal methods work. And I'm looking forward to what you have to tell us about this. So please, the floor is yours, Paula.
Thank you very much. Thank you very much for the very nice introduction. And also thank you very much for inviting me today. What I want to do is that I want to give an overview over our work on the formal verification of embedded system, exactly what you summarized so nicely. And in this talk today, I want to show you some ideas we had to overcome the problem that we usually have informally defined descriptions of embedded systems in practice in the industry. And also I want to show you some ideas how we can combine the forces of multiple analysis and verification techniques to increase the scalability of existing verification tools and for complex systems. So embedded systems are systems that are embedded into some technical environment. They are also sometimes called cyber-physical systems because they have this discrete controller part and the analogous physical environment. And we can find embedded systems or cyber-physical systems everywhere around us, in our homes, in our cities, also as the technological backbone of the Internet of Things. And these embedded systems are often safety critical. For example, if we look at smart manufacturing, where if one of these robots fail, the production needs to stop. So this is very expensive. And we also have things like medical devices or driver assistance systems where a failure may even endanger human life. So you can easily see that it is very important to ensure the correctness of these systems. And still in practice, even safety critical systems sometimes fail. So for example, in 2015, the US Aviation Authority reported on a bug in the Boeing 787, where basically an integer overflow could cause the whole generator unit to shut down every 248 days without a system restart. This bug was detected, so no harm done. But of course, generally, such failures of embedded systems can also have serious consequences. So the question is, can it really be so hard to avoid such things? And the answer to this question is yes, this is really hard because there is a significant gap between what is possible in theory and what actually happens in practice. So in theory, we have these very nice formal methods many of you are developing, and with those we can exhaustively check the safety of a system for all possible input scenarios and all possible behaviors. However, those are typically only applied to small examples or on high levels of abstractions. And in practice, we have in a single car already 100 control units with 100 million lines of code running of them. And there the quality assurance techniques of choice are still simulation and testing. And the main reason for this is that we have two major barriers preventing formal methods from being applied in industrial practice. And one is that the languages that are used in industrial embedded system design are neither clearly understood nor formalized, so they only have informally defined semantics. And the second problem is that the scalability of formal methods is often limited. So to overcome these barriers is hard, in particular for embedded systems, because embedded systems pose two major challenges: their heterogeneity and their complexity. So embedded systems usually consist of heterogeneous components, and they are developed with a diverse variety of heterogeneous models and languages. For example, because we have hardware and software components, also the network architecture, the middleware and stuff like this we need to consider. And also we have this, because we have this discrete control and the continuous environment. So many different models of computation are involved here, and the underlying semantics of the models and languages that are used is not clearly defined. So we have to cope with the heterogeneity with informally defined semantics. With respect to the complexity, embedded systems are inherently pretty complex because they are concurrent, reactive, and real-time dependent. And in addition, in the last decades, we have started to make the systems larger and larger. So we put large numbers of components and subsystems into one system, as we have seen for the car, and steadily increasing when we look at car-to-car communication or at the Internet of Things. And we have started to put embedded systems into ever more complex and dynamic environments. So when we move from a factory robot with one single purpose to a fully automated smart factory, or from an electronic stability program to a self-driving car, our environments become more and more complex. Yeah, and these are challenges we somehow have to meet if we want to make formal method applicable in industrial practice. And in the remainder of this talk, I want to give you an impression how we at least work on these problems. In the first part of this talk, I will show you our work on transformation-based automated formalization. So the idea is to overcome the problem of informally defined system descriptions of heterogeneous systems. And in the second part, I will then show some ideas to combine forces, to combine various analysis and verification techniques to cope with complex systems. And yeah, then I will conclude my talk. So I start with the transformation-based automated formalization of system-level design languages. And what I call system design languages are languages where we can design a heterogeneous embedded system within one language. Two widely used system design languages in the embedded systems industry are System C, which enables the modeling and simulation of both hardware and software within one language, and MATLAB Simulink, which enables modeling and simulation of dynamic systems. So it enables us to model a discrete controller together with its analogous physical continuous environment. Both these languages, System C and Simulink, come with powerful tool support and are used for model-based development. So the advantages here are that we can do early design space exploration and automated code generation, and also, of course, early validation. And System C is implemented basically as an extension of C++ with time and reactivity and other things we need to model hardware in the software description language C++, so hardware data types and modules and channels. And with that, it's a classical control flow oriented language. And Simulink, on the other hand, is a classical data flow or signal flow oriented language, where we have an extension of block diagrams with blocks that can model something like integrators or complex mathematical transfer functions such that we can model the dynamics of hybrid systems, for example. So these are two very different languages which are both widely used in industry and which both have a very specific execution semantics, and both have the problem that these execution semantics are only informally defined, which makes it hard to apply formal methods to them. Has been, of course, a lot of effort to overcome these problems and to provide formalizations for both System C and Simulink. However, at the time when we proposed our first transformations, the existing transformations required a manual formalization of a given design, or they supported only a small subset, or they produced formal models that are really hard to comprehend. And today, the situation has gotten better, although still all the approaches known, also our approaches are limited to some subsets of System C and Simulink. And in addition, the existing approaches, including our own, all suffer from the state space explosion problem. But I will get to the latter point, the scalability problem, later. And for now, concentrate on the underlying idea of formalizing such informally defined system descriptions automatically. And the underlying idea is that we take an informally defined system model as a starting point. And this informally defined system model has informal execution semantics. And what we basically do to make formal methods applicable to this informal system description is that we perform a semantic mapping from the informal execution semantics into some existing formal semantics. And from this semantic mapping, we can then derive transformation rules and some predefined component that capture the semantics of the informally defined language. For example, for System C, we define transformation rules that tell us how a while loop should look like in the formal language, or how a wait statement should look like in the formal language. And the predefined components tell us how the scheduler, the System C scheduler, or how a System C event can be represented within the formal model. And using these transformation rules and predefined components, we can then develop automatic transformations, which basically take an informal system description as input and generate a formal model from this. And by using existing formalisms, we gain access to existing verification tools. So this formal model can then be used to verify that a given requirement specification is satisfied, or if it is not satisfied, we typically get a counterexample which can be used for debugging purposes. So this is the general idea, and we have done this both for System C and Simulink with several formal models with several verification backends. For System C, we have developed transformations into 3 powerful verification tools, namely the real-time model checker UPAL, the bit precise SMT solver Euclid, and the software model checker CPA checker. And for Simulink, we have developed a transformation into Euclid as well for the discrete subset of Simulink, and into the differential dynamic logic, which is the input language of the theorem prover Chimera X for a hybrid system subset of Simulink. In this talk today, to show you how this works, how we capture the semantics of these informally defined languages, I will show you 2 transformations as an example, from System C to UPAL and from Simulink to Chimera X. For all of our transformations, we have 3 major advantages in doing this at all. And the first is that we say we define a formal semantics of the industrial system design languages by performing these mappings, by providing these transformations. We do not prove their correctness, but we say we capture the semantics precisely enough that we define a formal semantics in doing so. We derive the formal models fully automatically, so we spared the designer the tedious task of writing formal models himself. Some people like to do this, but not all designers like this as much. Of course, always only for a clearly defined subset. So we always have to see what is possible in the verification language. We cannot do dynamic process creation in or unbounded variables in UPAL, for example. However, if these assumptions are met, so if we look at the required subset and you can give us a System C or a Simulink design, we can automatically transform it. And with that, we gain access to existing mature and powerful verification tools, like, for example, the UPAL model checker. And this is also what I want to use as an example now to show you how these formalizations look like within how this actually works. And I start with the transformation from System C to UPAL. And to let you know briefly how System C works, System C was introduced by an industry consortium, the Open System C initiative, in 1999, and has since been approved in several IEEE standards, first in 2005. And System C is a very flexible languages supporting a number of models of computation, and in particular comes with a powerful concept for abstract communication. But today I really want to focus on the core semantics of System C to give you a feeling how we captured this execution semantics with our transformation. So the only things we need to know today is that we have some modules, for example, could be some wheel sensors or the electronic control unit, and they communicate via ports and channels. So the electronic control unit can read something from the wheel sensors via a bus. And from a semantic point of view, the semantics of System C basically boils down to concurrent processes that are executed within a discrete event simulation. So we can declare concurrent processes using some macro, here, for example, an anti-lock braking system. And these processes are then run by a cooperative scheduler. So they are run until they voluntarily give up control. And this process here, for example, gives up control by waiting for some event that tells that new speed information is available. So we execute until we meet this wait statement. Then we can read some new speed information from the bus, and then we can notify some other processes that we need to do something with the brake or whatever. And for these notifications, which is part of the expressive power of System C, that we can have immediate notifications, which just trigger other processes immediately, make them immediately ready for execution. We can also have timed notifications with an arbitrary time resolution, and we can have delta delayed notifications. The latter is indicated by the parameter 0, and it basically introduces a zero delay semantics, as you know from most hardware simulators. Maybe the idea is just that I finish the evaluation of all processes that are currently ready to run, but without increasing the simulation time, and then the event gets notified. Yeah, so this are the basics of System C. And with respect to UPAL timed automata, UPAL is a very powerful tool for modeling and verification of real-time system. It was jointly developed in the mid-90s, or since the mid-90s, by groups from the universities of Uppsala and Aalborg. Maybe you had the chance to listen to the very nice invited talk by Kim Larsen this Saturday at Memo Code. And the idea of UPAL is that we model concurrent systems as networks of timed automata, and timed automata are basically just finite state machines extended with clocks, and the concurrent process is synchronized on channels using binary or broadcast channels. So in this little example here, we can receive a request from some other automaton. If we do this, we reset a local clock X to 0, and then we can wait for at least min time and at most max time until we take this transition. So we can model time in a real-time dependent behavior in a pretty flexible way, and the clocks are running autonomously in the background, and UPAL comes with nice tool support for this, including a graphical editor, graphical animation, and also a model checker. So this gives us the formal methods here. UPAL also provides some extensions to the basic timed automata concept. So for example, data variables, which can be manipulated using a C-like host language, and it has urgent and committed locations. Urgent locations are just locations in which no time may pass, and committed locations also are urgent, but in addition, they have to be left before all other locations are left, so we can introduce priority with those. So this is in a nutshell how System C and UPAL works, and our idea is to bring this together to map a System C design into a UPAL representation is that we basically just translate each method into a timed automaton. We generally know how to do something like that, to translate a method into a timed automaton. And then most importantly, the interesting part here is that we provide predefined timed automata templates that precisely capture the execution semantics of processes, events, and the scheduler. I will show you how this works in a minute. And then we connect all these automata with synchronizations and shared variables. So from a high level point of view, concentrating on the course semantics right now, so this is a simplification, but generally in our resulting UPAL model, what we have the processes which may execute methods, and they synchronize with the scheduler by telling him that they want to be deactivated. So the cooperative scheduler means they deactivate themselves, and the scheduler can activate events, or they can wait for events. And for this wait here, we actually use a broadcast channel such that one event can release multiple processes waiting for it. And the scheduler informs the event if all processes have been evaluated, such that delta delayed notifications can take place. And in turn, the events inform the scheduler if some timed notification expired, such that time can be advanced. This is the high-level view. We are going to go into this right now. So let's first have a look at the methods, which, as I said, are pretty straightforward. We just take assignments as updates. So for example, here we have I assigned 1, and we take this as the transition here, and we model the control flow with guards. So some while loop with a loop condition is just becoming a loop here in the timed automata with the same condition. And for the core return semantics of methods, we can just introduce a binary channel mcontrol, which passes control to this method automaton, either if the corresponding process is triggered, if it's triggered within a process, or if it is just called by some other method. And we can also use global variables to, like this nparam here, to copy parameters to this method. So this is pretty straightforward, and it becomes interesting when we look at a wait statement, because this is where the execution semantics of System C is needed to know what exactly happens here. And what happens, how we have modeled this, is that the method deactivates itself and goes into the waiting state. So all other statements are urgent locations, no time may pass there, but now we go into a waiting state and wait for the event E. We are waiting for here as well, to be triggered, to be notified. And only if this event occurs, we then wait for the scheduler to be activated again. The variable readyprox is used here to just count the number of processes that want to be executed. And this significantly simplifies the scheduler, because within the scheduler, we just send this activate signal here as often as there are processes ready to run and wanting to execute. And we use the binary channel for activate here. And the semantics of UPAL says that for binary channels, if there's more than one communication partner available, we make a non-deterministic choice. So what we achieve by using a binary activation channel here is that we achieve a sequentialized but non-deterministic order of processes within the evaluation phase, which is exactly what happens in the System C semantics, or what should happen in the System C semantics. And this we, of course, for model checking, this means we have a complete coverage of all possible execution orders, and we can even detect bugs that are impossible to find with simulation here. Yeah, from this evaluate phase to go back to the scheduler, of course, we can have immediate notifications here, making new processes ready to run. They will just be increase the ready procs variable and then be activated as well. And only if there are no more processes ready to run, we switch to some update phase. I will not go into the details of this right now. Update requests are executed there also in non-deterministic order. And at some point, if all evaluations and updates are performed, we send this delta delay signal I've shown you before, which informs the events that they can now release delta delayed notifications because all processes at the current simulation time have finished execution. And then either new processes become ready to run with these delta delayed notifications, then we start a new evaluate phase, or there are no more immediate and delta delayed notifications, and then we go to an advanced time phase where we basically wait for the events to tell us that some timed notification has expired. So this is the second piece, and now the final piece of this core semantics of System C, the event template. This captures immediate delta delayed and timed notifications, and the idea is basically that if I have an immediate notification, I just immediately send a wait signal to all the processes that are waiting for this event by using a committed location here. We make sure that this happens before the scheduler can switch to another phase, can leave the evaluation phase. And we use a broadcast channel wait here to make sure that all processes that are waiting for this event are triggered by this. For delta delayed notifications, we use a different channel here because there we need a parameter T in addition, which should be 0 if it's a delta delayed notification, and we copy this parameter, which is passed via a global variable again, to a local variable notification delay. And if this notification delay is 0, then we have a delta delayed notification, and then we just wait for the delta delay signal sent by the scheduler when all processes have finished the current evaluation phase. And then again, we trigger all processes waiting for this event with a committed location. And finally, for timed notification, of course, here we finally exploit the timed in the timed automata. So if we get a timed notification, we reset some local clock X to 0, and then we wait exactly until the given notification delay expires by using an invariant here together with a guard, where we wait until X is exactly equal to the notification delay. And then we send advance time to the scheduler, which again, and again trigger the processes waiting for this event. Yeah, this is it. This is what I wanted to show you today, to show you how we model the execution semantics of System C in its core, in the discrete event simulation, the cooperative scheduling. Of course, in real transformation, there are a lot of other things to consider. So this is a simplification I have shown you today. For example, for the event template, we also have to consider concurrent timed notifications, or that pending notifications might be overwritten. So the final event template looks a little bit more difficult, but due to brevity and time constraints, I will not go into the details of this here. So to summarize, for this formalization of System C, what we do here is a fully automatic transformation of System C designs into a formal model, which enables a formal verification of safety, liveness, and timing properties with the UPAL model checker. Our transformation covers a comparatively large subset of System C, only also, although I have shown you a very small part of this today, we also support, for example, static and dynamic sensitivities and different kinds of threads and large parts of the transaction level modeling standard, including transport interfaces and sockets, and also a restricted use of pointers and stuff like this. Yeah, the models we generate are comparatively compact because we have this one-to-one mapping from methods to automata. And they are pretty well comprehensible. Of course, because UPAL is just very intuitive and has this nice graphical interface, but also because our transformation, although we need a flattened System C design because UPAL does not support hierarchy, we still keep the structure of the original design transparent to the designer by using prefixing, and this makes it very easy to understand where everything came from. Yeah, we also keep the line numbers and stuff like that to make it easy to track that back. Our transformation is licensed under GPL and freely available, so if you want to try that out, just go to my website and feel free to do this. We have evaluated our transformation with quite some case studies until now, and I just want to show you one example. One example was the transaction level model of the AMBA advanced high performance bus, which is used in many ARM-based systems and was provided to us by Carbon Design Systems. This is a design that was, of course, extensively simulated and tested by Carbon Design Systems themselves, but still when we translated it into a UPAL model and started the UPAL model checker, we were able to detect an error within this design, namely a deadlock situation, which occurred in the very rare case that a transaction must be split over the bus and there was a missing variable reset, so the whole system hung up if this happens. And this is a very good example for a typical corner case, which happens very rarely, but also is very hard to detect with simulation and testing. And with the UPAL model checker, we were able to detect this deadlock just in a few minutes. And thanks to our structure preservation and the graphical animation in UPAL, it was also very easy to find out what the source of the error is and to fix this bug. And then, of course, we have also verified some properties for a fixed version of the design, invariance from one master and one slave up to two masters and two slaves. And we have verified that the design is then deadlock free, that only one master is active at a time, that a master that requests the bus eventually gets it granted, that all transactions are completed within 200 seconds, if I remember correctly, that all memory accesses are type safe, and that there are no null pointer accesses. And we were able to verify all these properties in at most 2.5 hours. So that's pretty reasonable for a formal verification. And yeah, that's actually a very nice result. Still, of course, there's a reason why this table stops here, because if we connect more components to the bus, then the model checker cannot do that anymore, then it becomes infeasible. We cannot get a result in reasonable time. We go out of memory. So this emphasizes the scalability problem again, and I will get back to this later. But for now, I will also briefly summarize our formalization of Simulink very quickly, this time only highlighting the key ideas here. Again, in a simplified way to give you an impression how this works without putting all the confusing details of the Simulink semantics in this. So the underlying idea of our transformation from hybrid Simulink models into the differential dynamic logic, DL, the underlying logic of Chimera X, is that we target continuous and discrete blocks. That's why we call those Simulink models hybrid, and also control flow. So I want to show you the ideas with a very simple example, which is still a hybrid system because it contains these three kinds of blocks. And what we have here is a simple Simulink model that modeled the dynamics of a very simple car, and the position of the car is given at the output X here, and we compute the position of the car by continuously integrating, so this is a continuous block, over either the input velocity, so it can drive with a constant velocity, or over 0 if the car stops. And to switch between these two behaviors, we use a switch block, so this is a control flow block, and to kind of emulate, we have some discrete controller here. Use just a 0 order hold block in this example, the blue one here, which basically just takes a continuous signal as input and sampled this at discrete sample time. So this is basically just a discretization. And if we transform such a simple Simulink model into DL, looks like this. So what we basically do, we just map the discrete blocks to discrete assignments, and these shown here. So X is just passed to X hold, the input to the output. And we do this whenever we reach the discrete sample time. So whenever clock becomes greater or equal the sample time TS, then we do this assignment. And in our continuous evolution, so those are continuous evolutions in DL, we model that the time derivative of this clock variable here is 1. So it just evolves as the simulation time. And we make sure that we do not evolve further than the sample time, adding the condition clock less or equal to TS to the continuous evolution domain. Yes. So together, this means either we have reached the sample time, then we assign the input to the output, or not. In this case, we just do nothing with the X variable, the X hold output here. So this is the discrete block, and to model the continuous behavior of the integrator, we just use the time derivative in the continuous evolution. So we can have X prime equals 0 here, or X prime equals V in, the input velocity, and we switch between these two behaviors using a non-deterministic choice. This is the plus here, together with two test formulas, which basically model the switch condition. So we switch between these two behaviors depending on whether X hold, the output of the 0 or the hold block, is greater than stop or not. Yeah, and that's basically it. I mean, we have the input velocity, which can be some arbitrary discrete assignments at arbitrary points of time, meaning we basically can verify something about the system for arbitrary inputs. And of course, we have to have a non-deterministic repetition to model the simulation loop, so we can repeat this behavior arbitrarily often. And this gives us a formalization of the Simulink semantics for the very basic blocks. Of course, again, it becomes more complicated if we consider other block types as well, if we consider numerical approximations as well. Also, this transformation is freely available on my website, and you can have a look at the more complex models there. But for today, I just want to give you an impression how we do this and show you some experimental results again, of course. So 2 case studies we have used is a very simple temperature control system and the distance calculator component of a multi-object distance warner that was provided to us by partners from the automotive industry. And we have transformed these models and done interactive verification with X, and with that we were able to verify that the temperature is kept in range and no rapid switching occurs in the temperature control system, and that the distance calculator actually shows correct gain behavior and that no overflow happens. So we were able to deductively and interactively verify hybrid Simulink models. Of course, you can see here that this is really expensive because those models are really, really small, and still it took us quite some manual effort, 8 to 10 hours here. Of course, this is only a very rough estimation because it's highly dependent of the expertise of the guy doing this, one of my PhD student in this case. So, but it gives you a rough estimation, right? And you see, it's all very expensive, and this brings me to the second part of my talk. So our ideas to combine forces to increase the scalability of the formal verification of embedded systems. And I will start with our approach for the automated petitioning and combined verification for System C. This is from a project founded by the German Research Foundation, the Rescue Project, and the idea we pursued there, the idea we developed there was basically inspired by classical hardware software co-design approaches, because what we usually do is in hardware software co-design that we combine subsystems on various levels of abstraction, and for example have a bit and cycle accurate hardware model together with an abstract model of the software, or the other way around. And we use this as an inspiration to follow the idea that we can automatically partition a given System C designs into sub-models that focus on certain aspects, and then safely abstract from the rest of the system. So the idea was that we can derive submodels that focus, for example, on timing and communication, but abstract from the behavior of the hardware and the software, and the same for asynchronous hardware and asynchronous software and synchronous hardware and so on. And these submodels are safe over approximations of the original system, because we safely over approximate the influence of hardware and software on timing and communication here, but still, which makes them pretty complex as well. But at least we can now transform these submodels separately into the verification backends, and in doing so verify partial requirements on each submodel with the verification tool that is best suited for it. So for example, a model that focuses on timing and communication with the real-time model checker UPAL, or synchronous hardware with SMT solving and co-induction, and so forth. And to achieve this, to compute such a petitioning and perform the abstraction automatically, we have developed an analysis which takes a System C design as input and basically computes all the dependencies that are present within the design as a System C dependency graph. And we use then this System C dependency graph as a basis to cut out submodels and compute an abstract verification interface for them. And how this works, I want to illustrate with an example of an anti-slip regulation and anti-lock braking system. This is basically a system that measures the speed at each wheel, and these by a tick sensor, and we have a tick counter here which counts these ticks and sends the result to the electronic control unit, which executes control algorithms, so an anti-lock braking system ABS and an anti-slip regulation ASR, and then sends some commands to the brake, some brake pressure that should be applied. And we have used this example as a case study also for our System C to UPAL transformation in 2015 already, but we have deemed it unverifiable due to the state space explosion problem. So the aim was now to compute petitions that can be handled via model checking. And to achieve this, we have computed the System C dependency graph. And I will show this System C dependency graph for some of these processes here. So we will look now at the tick counter at the front left wheel and the count and send process there, and on the read process that reads the ticks from the front left wheel, and the anti-lock braking system on the electronic control unit. And the System C dependency graph looks like this. And I will not go into all the details of this, but what is important here that we capture all kinds of dependencies in this System C dependency graph. So we have direct control dependencies, like the control flow graph of each process, together with methods that are called by this process. For example, if it writes something to this channel here, we have indirect control dependencies, because we can request updates that are then executed later. We have sensitivity or timing dependencies. For example, we can wait for a read event or for a write event within And we also have the classical data dependencies. So for example, the send process reads the number of counted ticks from the count process. And what we basically do for our petitioning is pretty simple. We just keep together everything which is a control or timing dependency. So we put all the processes that have really interdependent executions, whose control really depends on each other, into one petition. And this gives us one petition which contains the channel itself and the processes that are reading to and writing to and reading from the channel, but the processes which are not directly involved into the communication are put outside of the petition. And now we have a petition we want to separately verify, but we use an over approximation of the rest of the system. And for the velocity and the acceleration, we don't need this because they are written somewhere but not read within this petition. But the ticks variable, this is written outside of the petition. So we need an over approximation for this. And to get a safe and still small over approximation, we perform a classical interval analysis here. And the interval analysis basically tells us as a result that the ticks value is never used within the communication system. So the ticks are basically just passed through. And so we can compute one equivalence class for the ticks variable here from -infinity to +infinity. And when we assign arbitrary values to the variables that are written outside of the petition, we can just replace this by one constant value for the one equivalence class that is there as an abstract type. And this, of course, significantly simplifies the verification because we now have only one constant ticks value representing an arbitrary assignment. And with this, we were able to verify that the communication architecture actually satisfies some crucial properties. For example, that there is no deadlock within the communication architecture, that all ticks are eventually received, and that all ticks are received within 20 milliseconds. And we were now able to verify this in reasonable time for the communication between all four wheels and the electronic control unit. And this, of course, was not able for the full system. So we exploited the fact here that the input ticks can be fully abstracted at each wheel in this example, and this will, of course, not always work. You will not always find such an easy abstraction automatically, but in this case, a full state space exploration and model checking became feasible, at least for a partial model. We also tried to verify the control algorithms independent of the communication architecture with the CPA checker to not only combine analysis and verification, but also everything with other verification tools. Yeah, but we have not been successful so far in this. We're still working on this. Yeah, so this is how we achieve a combination of forces for System C. And for Simulink, we have chosen a different approach because for hybrid systems, it's really hard to compute abstractions automatically. So instead, we followed a manual approach there, a contract-based approach, basically. And what we just did is to introduce the notion of services for Simulink to ease the definition of contracts for Simulink designers. So the idea is that we use our transformation from Simulink to DL as a starting point, which enables us to use Chimera on Simulink model. And what we basically did is we defined this notion of services within a Simulink model, where a service is basically just a group of blocks which perform some joint functionality together, and whose behavior, whose externally visible behavior can be described by a hybrid contract. So these services here can be described by a hybrid contract. And we use this for compositional system verification as usual, as in every assume guarantee style verification approach, by just replacing the services, the concrete group of blocks, with their hybrid contract with an abstract description of their their externally visible behavior by abstracting from the inner workings in the DL model, and thus have a much more abstract and easier to verify system model in DL. Of course, we then need to additionally verify that each service actually adheres to its hybrid contract. So we cannot rely on the designers just writing the hybrid contracts absolutely correct from the beginning. And for this, we can again use our Automata transformation into DL and Chimera X. But here now we can also, because these contracts really separate the verification problem for single services from the system verification, we can also combine this with other verification tools. So for example, for purely discrete services, we can verify that they adhere to the hybrid contract using the Simulink design verifier, the in-house solution by the MathWorks, or by using our transformation to Euclid or something like this. And we can also, if there are some services which are just too hard to verify, we can also leave them unverified and only verify the overall system under the assumption that the service behaves according to its hybrid contract, and then use a runtime monitor to enforce or at least ensure that the service behaves according to its hybrid contracts or go into a fail-safe mode otherwise. Yeah, so again, this approach enables us to combine the strengths of various verification tools, and we have again done some experiments with this, with a more complex temperature control system, which now has two services within, again, verified the same properties, but now even though the system is much larger, the manual effort was less. We have also used the generic infusion pump to evaluate our approach to combine Chimera X with the design verifier, and were able to verify some services which were purely discrete with the design verifier and the overall system, and some other services with Chimera X. And we have verified there that a critical dosage is never administered and that we actually receive a warning on an empty tank. Yeah, 25 hours for this. And we have now verified with this compositional approach the full multi-object distance warner provided to us by partners from the automotive industry, where the services basically was the distance calculator we have verified before. And as we already have verified the correct gain behavior and that no overflow occurs for these services before, we can now verify it for the overall system with the contract-based approach within Chimera X, because there is nothing discrete there. Yeah, and we have recently also verified an autonomous robot that uses reinforcement learning to move within factory setting with moving obstacles and dynamically assigned goals. And we have verified collision freedom of the overall system under the assumption that the learning component behaves according to its contract. And we combine this approach with runtime monitoring to basically ensure that the reinforcement learning component can always only take safe actions that are safe with respect to the contracts. If you're interested in more details about this, I recommend the talk of my PhD student, Julius Adelt, who will present the paper where we presented this approach tomorrow in the hybrid systems session. Yeah, and so what we achieved here is that we now enable a combined verification of hybrid Simulink models with various verification tools. And yeah, the systems are, of course, still not what we need in industry, but we're getting somewhere, we are getting better. And with that, I want to conclude my talk. So what I have shown you today is our transformation-based formalizations. So I have shown you how we can use transformation to define formal semantics for subsets of the industrially used design languages, System C and Simulink, and how we can enable formal verification with existing verification tools using such transformations. And I have also shown you our more recent work on combining forces and how to analyze and partition System C designs into submodels. This can be done fully automatically, but it is, of course, heavily dependent on the fact whether we find a good abstraction automatically or not. And I've also shown you our service-oriented verification approach for Simulink, where the contract, the abstractions have to be provided manually. Which makes better abstraction possible if you can find them. So this is also one of the open challenges I want to point out. I think we have to improve the support to find the right abstractions for embedded systems we're looking at, either by investigating better analysis technique that find that out for us automatically, or if the designer has to do something manually, we at least should help him by making contracts reusable, by maybe providing something like a contract pattern for the verification of embedded systems and things like this. And of course, I have to admit System C and Simulink are used in industry, but of course we are still on a comparatively high level of abstraction here. So the final implementation running in the embedded system still remains unconsidered. So what is also needed for the future to really apply formal methods in industrial practice is that we need more support to close the gap between our verified models and the final implementation, for example, by improving the support for real-time operating systems and also by improving the integration of formal methods and testing. I know that there has been done a lot in this direction and there already exists a lot of great results, but I think we can still improve on this. Yeah, and with this, I thank you for your attention and would be very happy to take some questions right now as much as the time allows, and also in the coffee break after, of course.
Okay, thank you very much, Paula, for this interesting talk. So I do an applause for everybody.
Thank you very much.
I see other people saying also very nice keynote, and I see people raising hands. So maybe Andre Platzer, maybe you could ask your question.
Thanks, Paula, for a wonderful talk. I really enjoyed it. I do have a question and a comment. The one is that 790 Simulink blocks is a lot, so you're perfectly forgiven for having needed some manual effort along the way. That's perfectly fine. If you're monitoring a part of the design at the end of the day, you may actually benefit from the Modelplex technology. It's also part of the Chimera X theory improvements.
We actually used this. Sorry, I forgot to mention it. This is the great advantage of using Chimera X here, because we can even generate the runtime monitors automatically, right? Thank you very much for adding this.
And they do have a correctness proof. That's cool. And then my question is, how worried are you about misunderstandings in formal System C and Simulink semantics by, for the tool vendors, you as the verification tool provider, and the user at the end of the day? And the reason I ask is, of course, that Simulink a few years ago used to have a semantics where the meaning of a Simulink model depended on the XY coordinate where you put the stupid blob in, which is yes. Logic and programming language people give up and scream in terror. So how are you mastering these challenges?
Yeah. Well, this is difficult, of course. Still, sometimes we do a lot of validation, and it's very difficult to understand the semantics of System C or Simulink in the first place, and sometimes also they have bugs as well, right? So something that in the simulation happens doesn't generate code, and we ask ourselves, okay, what should be the execution semantics be here? And as I said, we also found bugs in the System C reference implementation. I think the way we work is not really a rigorous approach, right? We're kind of re-engineering the semantics here and improve the possibilities to debug. But yeah, I would be pretty confident that our System C semantics is correct, because we have worked with this for so long now. And but for the Simulink semantics, I have to admit I'm still not that sure, because there are a lot of issues in the semantics where the documents are not clear at all, and also the simulation sometimes doesn't really reveal what is happening there in detail. But I think that these formal approaches help there as well. So by capturing these semantics and by developing these transformation rules, we gain a better understanding of what is happening and what should happen, and maybe also help the tool developers like MathWorks to better define their semantics. I hope that answers your questions.
It absolutely does. And I think you have all the rights in the world to say, well, you're helping with the rigor that MathWorks' stateful Simulink ought to have had, right? So that's super useful. Thank you.
Thank you very much.
Well, thank you. Then we can move on to Thomas Santen, who also has a question for you.
Yeah, thank you. Yeah, Paula, thank you very much for a very nice talk. Enjoyed it very much. The short version of my question is, where do the properties or the contracts come from? And of course, we can make that a little bit more elaborate. I can see where they come from as you just look at standard properties like backlog freedom and these things. What I'm a little bit worried about is how would an engineer formulate properties in the formalized version of the system. I mean, this is what the properties have to relate to, right? Do we have any ideas or work around that already, or is it also an open challenge?
This is also an open challenge. I actually would summarize this under the point of finding the right abstraction, right? Because I mean, the writing down the property itself is kind of, I mean a contract is a property and a description of the behavior at the same time, I would say, right? So yeah, I mean for the UPAL transformation, for example, of course, I think we use a subset of CTL there, which UPAL supports, and this is pretty well understood for the designer, but as you correctly guessed, it's good for the standard properties we typically have. But if we come to more complicated functional properties, it gets difficult. And this is also something we are struggling currently with the CPA checker, because we can build these nice observer automata there, which help us to define more complex functional properties. But it's really difficult in the process. We sometimes don't know anymore whether our system is wrong or we have expressed wrongly what we want to have. So yeah,
exactly.
absolutely.
That's exactly my point. Yeah, I mean, you have to debug the properties as well, right? You don't get them right in the first go usually. So and that may be maybe a little bit less work, but it may be substantial work to get the properties right as well.
Yeah, absolutely. And the open challenges I named here is just a very incomplete list.
I can guess that. Okay. Anyway, thanks a lot for the talk.
Life would be so boring if we had no open challenges, right?
Yeah.
Yeah. So
I don't think that will ever happen.
Yeah. I see two more people that have raised their hands, and after that we go for the coffee break. So Jonathan, Julian, Huerta y Miniva. I hope I pronounced that correctly.
Yeah, thank you. That's correct. So this is very nice work. Thank you very much for your talk, and it's exciting. But now I wanted to ask, related to the presentation yesterday by Stefan, Mitch, and Alexei. They mentioned that one of the problems with the formalization was that whenever you go from the formal model to the implementation, you miss on these delays in transmission of messages between controllers. Do you think that your automatic translation from System C to the formalization would help to deal with that?
Yeah, well, I mean, from System C, we go not into the differential dynamic logic. Just
sorry,
clarify this point. And this is much easier with UPAL, actually, so it would be easy to answer the question there. Yeah, for the Simulink transformation to differential dynamic logic, actually what you have to do to do timing in a useful manner is that you have to add numerical approximations by allowing the time to always go a little bit further. But this means that we are over approximating the timing behavior a lot. So I did not mention this, but we also restrict ourselves to safety properties here. This is also inherent in the transformation because we over approximate the system behavior. And this also means that there are probably a lot of properties we just cannot prove because our over approximation is too rough for them, to coarse for them. We haven't worked with this for such a long time as we did with System C, so we are still new to this and trying things out. So I think I cannot actually answer your question with more than, yes, this will be complicated.
Okay, yeah, that's expectable. Thank you.
Okay, and so Najun, you lowered your hand, but you still have a question?
Yeah, I want to ask one question. Hi, Paula, thanks a lot for your interesting talk. So my question is that in your approach, you see at the formal model side, formal model is given by the System C and the Simulink. I guess the two parts should interact each other, right? So I didn't see how to interact between the two parts. Also, at the formal model side, you see that Simulink part is formally defined by using differential programming or differential logic. System side is formally defined by the U-part or timed automata. So I didn't see how to interact between the two formal models. So can you say something that?
Well, we do not interact between the models of System C and Simulink, right? We just try to, within the System C world and within the Simulink world as two separate things, we try to find a way to kind of concentrate on certain submodels. I don't know whether I understood your question correctly. So for System C, we do this partitioning, and for the interactions between submodels, as I said, we compute those over approximations. And this works nice in some cases, as for the TIX variable, but in other cases, of course, it might also make things even more complicated or things impossible to verify because the property does not hold anymore if we just allow arbitrary behavior around the submodel, right? So yeah, this limits the use of it, but still, I think there are a lot of practical examples where it actually works and where you can find a good abstraction and then verify some properties. And for Simulink, we leave it all to the designer, right? The interaction between the services. I mean, the final system does not only consist of the services, but basically of a Simulink model where we replace some subsystems by a hybrid contract. So we kind of keep the overall interactions because we have the overall Simulink model there, but replace single services by the abstract behavior. Okay, I'm not sure whether this answers your question completely.
Yeah, I see. Okay, I got your point. Okay, thank you.
Thank you very much.
So thank you all. So once again, Paula, thanks very much for this interesting keynote. If people would still like to have a chat with Paula or with some of the other participants, please join us in wonder.me, the coffee space. The next session will start in approximately 10 minutes. So Paula said she would be here in this coffee break, but she also has to chair the next session, right? But she will be there in other coffee breaks as well. So if you would like to have a chat with her, please join us there. And yeah, so we start the next session at 20 past in 10 minutes. And thanks for now. Thanks a lot, Paula.